Hi students, please subscribe my channel Nana. Thank you students. In today's section I am going to discuss about the CFT Nana crystal field theory coordination compounds lesson Nana 12th class. In octahedral complex I am going to discuss Nana splitting of d orbitals in octahedral complex, octahedral field. Clear? So splitting of d orbitals in octahedral field I'm going to discuss you students. See here. So first I am going to take d subshell Nana. In d subshell how many orbitals will be there Nana? 5 orbitals will be there. Okay, 5 orbitals. These are named as dxy, dyz, dzx, dx square minus y square, dz square. Okay, total 5 orbitals. So these 5 d orbitals are called degenerate orbitals. What is meant by degenerate orbitals? These 5 orbitals are having the same energy students. That's why these 5 orbitals are calling as degenerate orbitals. All orbitals have same energy. Clear? So these are all having the same energy. Now coming to the structure students, shapes of these orbitals dxy, dyz, dzx. See here, these are the three orbitals dxy, dyz, dzx orbitals shapes Nana. We know that d orbital shape is double dumbbell. So this is a double dumbbell shape. These are the lobes Nana. These lobes are present in between the Cartesian axis. In between the Cartesian axis. Are you clear? So this three orbitals are these three orbitals are non-axial orbitals. That means the lobes are present in between the Cartesian axis. Correct or not? So that's a non-axial. Okay, that means these lobes are not present along the Cartesian axis. Okay, they present between the Cartesian axis, between the x and xyz axis. Are you clear? That's why we are calling as non-axial orbitals. So in the octahedral complex, these three orbitals are named as T2G orbitals. What we are calling? T2G orbitals, Rana. T2G orbitals. Now coming to here, remaining two. Dx square minus y square, dz square. See here, these two orbitals are axial orbitals students. Axial. That means these lobes are present along the Cartesian axis. Correct or not? Along the Cartesian axis. So that's why these two are calling as axial orbitals. These two orbitals are named as EG orbitals. Are you clear? So non-axial orbitals, these three named as T2G orbitals. These two orbitals are named as EG orbitals, Nana. Okay. Now see students, here now I am going to discuss splitting. See here. So this is the octahedral complex. We are discussing the splitting of d orbitals in octahedral complex. This is the octahedral complex. Total 6 ligands are present around the central metal atom. Now see here, these ligands, how they are Nana, along the Cartesian axis. Correct or not? These ligands, 6 ligands are placed along the Cartesian axis. Yes or not? This is x-axis, this is y-axis, this is z-axis. Okay, that means 6 ligands are present along the Cartesian axis. Okay, next dxy, dyz, dzx, these three orbitals what we named T2G, non-axial orbitals. These two, dx square minus y square, dz square orbitals are named as EG, axial orbitals students. Are you clear Nana? Axial. Okay, so all ligands are axial. All ligands are axial only now along the Cartesian axis there. Are you clear students? All ligands are along the Cartesian axis. Okay, these 3 points understood Nana. Now see here. So these ligands are ready to donate the electrons to the central metal atom. Metal atom is ready to accept the electrons. So whenever these 6 ligands come closer to the central metal atom students, so these 6 ligands, whenever come closer to the central metal atom, what happened? In the metal atom, d orbitals will be there. In d orbitals, electrons will be there. In ligands also, electron pairs are there. Electrons will be there. So whenever ligands come closer to the central metal atom students, what happened? In ligands electrons, in the central metal atom electrons, what happened? Repulsions are taking place, Nana. Are you clear? So because of repulsions, what is happening Nana? What is happening here? T2G orbitals non-axial, and Eg orbitals, axial orbitals. Okay now, so whenever 6 ligands come closer to the central metal atom, repulsions are taking place. That means because of these repulsions in the metal atom, 6 in the metal atom, 5 degenerate orbitals loses their degeneracy, students. Are you clear, Nana? So whenever 6 ligands come closer to the central metal atom, in ligands electrons will be there. In the central metal atom also electrons will be there. In between the two electrons, what happened? These two electrons, repulsions are taking place. Because of these repulsions in the metal atom, the total 5 d orbitals loses their degeneracy. Before that, they degenerate orbital. That means they have the same energy. So because of these repulsions due to the ligands, what happens, students? They loses their degeneracy. Are you understanding? That means the total 5 d orbitals split into two sets of orbitals. Okay, now one is lower energy orbitals, another one is higher energy orbitals. Are you clear? Okay, now see, 6 ligands are present along the Cartesian axis. These are axial, correct? All ligands are axial. Now which are axial in the metal atom? In metal atom, 5 d orbitals which are axial. Eg orbitals are axial. These two orbitals are named as Eg. These are axial. That means Eg orbitals of the central metal atom and 6 ligands both are in the same plane. Are you correct? Are you understanding, students? 6 ligands and in the central metal atom, Eg orbitals. Because Eg orbitals are axial, 6 ligands are also axial. So that's why these both are same na, axial. Are you understanding? So that's why in the metal atom, these two Eg orbitals are axial and 6 ligands are axial. Both are in the same plane. Are you understanding? So that, and next T2G orbitals where there in between the Cartesian axis. Are you understanding, students? In between the Cartesian axis, T2G orbitals like this. Are you clear? So in between the Cartesian axis will be there. These are non-axial orbitals now. Now see, students, whenever 6 ligands come closer to the central metal atom, here in the metal atom, Eg orbitals, ligands, both are in the same plane. So that's why here all ligands are strongly repelling the Eg orbitals of the central metal atom. The 6 ligands repelling strongly Eg orbitals of the central metal atom than the T2G orbitals. Are you clear? Because T2G orbitals are not in the same plane of ligands. Are you understanding? They are in between the Cartesian axis. Are you clear? So they are not in the same path. So that's why these 6 ligands are strongly repelling the Eg orbitals because both are in the same plane. Eg orbitals energy is raised, students, because of 6 ligands repulsions. Are you clear? So these 6 ligands repelling strongly Eg orbitals than the T2G orbitals. Hence their energy is raised. Which energy? Eg orbitals energy is raised. That's the Eg orbitals goes to up and T2G orbitals comes down. Are you understanding? Because their energy is increased, these energies decreased, students. Now here I will see you, Nana. Total 5 d orbitals. These are the 5 degenerate orbitals, students. Degenerate orbitals, nothing but what, Nana? They have the same energy. Okay now, so these are the degenerate orbitals. Now these degenerate orbitals are named as dxy, dyz, dzx. Okay, next dx square minus y square dz square. Clear? Total 5 orbitals. These are named as degenerate orbitals of the central metal atom. Now these orbitals, whenever 6 ligands are come closer to the central metal atom, these 5 degenerate orbitals loses their degeneracy because of repulsion, students. Are you clear? So see, in ligands electrons, so in this metal atom d orbitals electrons between the repulsions are taking place. Because of these repulsions, they loses their degeneracy. Now see here, these are losing their degeneracy. These are non-degenerate orbitals. What we are calling? Non-degenerate orbitals. That means they loses their degeneracy because of repulsions. Are you understanding? Loses their degeneracy, and these orbitals are split into two sets, Nana. See here, what are the two sets? These orbitals are split into two sets. First one is, which orbitals energy is increased, Nana? EG orbitals, correct? These two EG orbitals. Understanding EG orbitals, so ligands both are in the same plane, axial. So that's why EG orbitals are strongly repelled by the ligands. That's why their energy is increased. That means EG orbitals goes to up. EG means how many orbitals? Two orbitals. Dx square minus y square dz square. So I am taking here two orbitals. This one, what is the name, Nana? This one, d x square minus y square. This is dz square. Clear? So these two are the orbitals. These are which orbitals? So eg orbitals. And next, t2g orbitals, where they are not in the same path, correct, same path of the ligand, so these are non-axial, so that's why their energy is decreased. That means these t2g orbitals comes down. So T2g orbitals, these three orbitals in T2g, how many orbitals are there? 1, 2, 3. Total 3 orbitals. Names, Nana? dxy, dyz, dzx. Are you clear? So these three orbitals energy is decreased, students. Are you clear? So decreased. These orbitals comes down, these orbitals will go to up. Total 5 orbitals are split into two sets, Nana. Now from here to here, this is the crystal field splitting energy. What we will call delta naught. What we will call, Nana? Crystal field stabilization energy. Crystal field stabilization energy, Nana. Are you clear? This is CFSC, crystal field stabilization energy, in the case of octahedral complex. That's a delta naught. Here naught indicates what, students? Octahedral complex. Delta naught indicates octahedral complex. Okay, now. So what is the crystal field stabilization energy, students? It is the energy difference between the two sets of d orbitals. This energy gap between the two sets of orbitals. Are you clear? Energy gap between the two sets of orbitals is called delta naught. Okay. Now I want to calculate energy of these orbitals and EG orbitals. What about the energy of T2G? These are which orbitals? T2G orbitals. Okay, now I want to calculate the energy of T2G orbitals, EG orbitals. Now, first of all, EG orbitals energy I am calculating, Nana. EG orbitals. Total how many orbitals in D subshell 5 na? So total 5. That's why take this number in the denominator, Nana. In the numerator, this energy is rising now. That means value is positive. It is increased kada, positive. So positive take. In the numerator, what you have to write? How many orbitals energy is decreased? 1, 2, 3. That number you have to write in the numerator, and you should take the delta naught. 3 by 5 into plus 3 by 5 into delta naught. So this is the EG orbitals energy plus 3 by 5 into delta naught. How to write? Understood, Amma? Total 5 d orbitals. In 5, out of 5, how many orbitals energy is decreased? 3 orbitals. Here positive, why we are taking? Because their energy is increased. And coming to here, T2G orbitals. What is the energy of T2G, Nana? Tell me. These orbital total how many orbitals? So take that number into take that number in the denominator, and these orbitals energy is decreased now. That's why we have to take minus, Nana. We have to take minus Nana. So here in the numerator, how much you have to take, Nana? Total how many orbitals energy is increased? 1, 2. Total 2 orbitals energy is increased. So that's why minus 2 by 5 into delta naught. Are you clear, students, how to take? Here total 5 d orbitals. These energy is decreased, that's why we are taking the minus sign. How many orbitals energy is increased? 2, 1, 2, 2 numerator you have to take. When you are writing this energy, you have to consider these 2 orbitals. When you are writing this energy numerator, you have to consider this one. Are you clear? So plus 3 by 5 into delta naught minus 2 by 5 into delta naught. What is the answer? 3 by 5 into delta naught means what is the answer? Plus 3 by 5 is nothing but plus 0.6 into delta naught. Plus 0.6 into delta naught. This is the energy of Eg orbitals. What is the energy of T2g? Minus 2 by 5 is nothing but how much we can write? Minus 0.4 into delta naught. Are you clear? Minus 0.4 into delta naught. 2 by 5 na 0.4 into delta naught. So this value had to multiply with delta naught, crystal field stabilization energy. Are you clear? So what is crystal field stabilization energy? Energy difference between the two sets of d orbitals is called crystal field stabilization energy. Understood, Amma? So like this, the d orbitals are split into two sets, Nana. In the case of octahedral complex, students. I hope you like this video. If you like this video, please like, share, comment and subscribe my channel, students. Thank you, students.